Hello, my name is Eric Normand, and these are my thoughts on functional programming. So, the thought I was having was about composability and algebraic properties. So, in school we learn about a few algebraic properties. We learn about commutativity, we learn about associativity, we learn about the identity of addition, which is 0, and the identity of multiplication, which is 1. And these apply very well in functional programming. And I think not so much because they are mathematical ideas, but more because their expression is so simple. Their definitions are so simple that they really focus on how things compose. And what mathematicians have done is figured out a bunch of ones for mathematical operations, like addition is associative and commutative, multiplication likewise, and when you have that, you have these very simple ways of saying how addition composes with itself, right? Now, when we're building abstractions in a functional language, because our primary means of building a program from smaller parts is composition, we want to focus on how things compose first and foremost. And so I believe it's important to define up front how things compose before you implement the thing. So what do I mean by that? I would say that if you want to define an operation, let's say so I have an example that I give in a presentation that is, you want to define a way to rotate an image and also translate the image, so move it around on the screen. You want to define how they compose. Does translate and then rotate, is that different from rotate than translate? What if I do 2 rotates or 2 translates? How do they affect each other? And by thinking that through before you start implementing the thing, and even battening those things down with testing, then you will be able to, you can guarantee up front that they compose in the way you're expecting. Now, mathematical definitions, mathematical properties are not going to give you everything you need, because they're kind of analyzing existing properties of existing operations. They're not engineering, they're not designing new operations so much. And so what you want to be able to do is take the lessons from those algebraic properties. And the lessons that are the most important are that they have very simple expressions. You can do with 1 or 2, with this expression is usually an identity, meaning an equality. So you say rotate then translate is equal to translate and then rotate, right? Or you say for idempotence, A or f of A is equal to f of A. right? So you're saying how it composes with itself with, you know, multiple invocations of the same operation. And what this lets you do is, because these are simple ones, but you can define new ones, because there's no algebraic property that there's few algebraic properties that relate to. So there's like the reverse or the inverse, something like that. Ooh, gotta cross the street. But there aren't as many as you would want. But what's important is that it's simple, that it's a very short expression, and that it defines how things work. So, you know, the other thing that you can play a little bit looser with is the notion of equality. Because very often in software we use an if statement to reduce the scope of when something is applicable. So what do I mean by that? So in general, adding an item, a key value pair, to a hash map is not commutative. So the assoc operation in closure is not commutative, because if you add the same key, so if you add the key A with the value 1, and then you add the key A with the value 2, the 2 will overwrite the 1. So the order matters. Whichever one comes second, that's the one that gets kept. So they're not strictly equal. But you can say, well, I know in general that's true. It's not commutative. But in this particular case, I know that I'm never going to collide keys. Right? You can make that assertion. It's kind of like a runtime assertion that in this case I will never collide keys. And so then it becomes commutative again, because if you never collide keys, you never have that overwrite situation, and then again it doesn't matter what order you put stuff in. Now another thing you can do is you can say they might not be equal, but they're still both valid. They're still both correct. Right? So if I do A1 and then I do A2, so the result is A2 is stored in that map, I could say that's a valid result. But also I could say A1 was a valid result as well. That can happen too, where you're not comparing them on strict equality, but on something else, like there's no contradiction. They're both equivalent. So like for instance the timestamp. Sometimes you don't care about the exact timestamp. You just want to know that it's after a previous one. Right? So that's a way of saying it's consistent, it's valid. They don't have to be equal. Strictly equal, like that. So there's ways of using these properties where they're not strictly defined the way they are in mathematics, that they can be defined a little bit more loosely, that two things could be commutative modulo I know that there's no key collisions, or modulo the timestamps don't matter, or modulo they're both consistent. All right, so I'm probably going to talk more about algebraic properties. I just wanted to get that idea quickly out there. Thank you so much. Hit subscribe, and I'll see you later. Bye.